Good morning everybody. So, today we will continue with this rate process, and the topic is complex reactions. Okay. So, we have talked a lot about complex reactions. We will conclude this session. So, some more aspects are still to be talked about. So, let us do that. So, we will talk a little more about catalysis and catalyst. So, what is a catalyst? I already talked about in earlier one of the earlier lectures. Now, basically catalyst is a substance that speeds up the reaction without the same being used up in the reaction. That is, somehow it speeds up, that is somehow it quickly helps in attaining the equilibrium, that is the forward reaction rate as also the backward reaction rate is influenced, and as a result of which the overall reaction rate is modified. And enzymes are also biocatalysts. These are called biocatalysts because biological molecules are used here. Now, if we think of catalysis, it can be of two types. One is homogeneous catalysis, that is the catalyst is in the same phase as the reactant, and the other one is the heterogeneous catalysis, where the catalyst and the reactant, these two are in different phases. Maybe one is in solid phase, maybe your catalyst, and your reactant may be in gas phase. Okay. So, homogeneous gas phase reaction catalyzed by solid surface can be an example of heterogeneous catalysis. Let us move on to the basic mechanism of catalysis, that is how catalysts work. Now, the thing is that I already mentioned that catalysts allow reactants to proceed, reaction to proceed by a different mechanism, okay, having a new pathway, and this new pathway has lower activation energy compared to the original one. Recall one of the earlier lectures. Okay. Now, the new pathway, since this new pathway demands less activation energy, so as a result of which more molecules will have, means more molecules, since it has got less activation energy. So, on an average more molecules will remain in the activated state, okay? And therefore, what is happening that the net reaction rate is influenced. So, more molecules will tend to react to produce your desired product, but it does not change the overall energy change associated with the chemical reaction. Energy change means maybe enthalpy change or maybe other energy form. Other energy form means maybe internal energy or something, maybe like free energy. These are not changed because the product and the reactant, these two states are remaining same. Only thing is that the activated state is getting a little modified, and as a result of which your this overall reaction rate and the overall activation energy is reduced. So, and the thing is that it shows up as a reactant in one of the elementary steps maybe, and also it is acting as a product in a later step. Maybe suppose you have got say an elementary reaction of this form, say A plus catalyst producing something, say B, okay. Then B is giving rise to your product plus catalyst back. So, here in this elementary step this is acting as a reactant, and in this step it is acting as a product, okay. So, they are involved, these catalysts are involved in one of the elementary steps where it is acting as a reactant, and maybe in another elementary step later time where it will it will appear in the right hand side. Next, let us think of heterogeneous catalysis. Say this is your surface. Sorry, this is your metal surface on which this reaction is taking place. So, this is your surface, metal surface, and this is hydrogen molecules, I mean dihydrogen molecules. Okay. So, these dihydrogen molecules are, maybe some of them are close to the surface and some of them are a little apart, and this will collide with the surface and will form a bond, I mean will form two bonds maybe. Okay. So, the metal, it is called that the metal, I mean this hydrogen is adsorbed on the metal surface, not absorbed. That is, the concentration of hydrogen onto the metal surface is high, and inside the metal, I mean the bulk of the metal is not that much. Okay. So, they are adsorbed, that is, they form bond with the surface of metal. Okay. And maybe what will happen, that there is a breakage of bond, breakage of this hydrogen original single bond gets broken. So, now what is happening, that after this bond is ruptured, so there is one isolated, I mean bound hydrogen atom, there is another bound hydrogen atom onto the metal surface, and they are just like nascent hydrogen, having tremendous amount of reducing capability. Okay. So, if it gets second component, I mean second component like some say unsaturated hydrocarbon, say ethene, that is ethylene, C double bond C, then these two hydrogens will quickly attach to that double bond, producing a saturated carbon carbon linkage. Okay. So, think about that we have got this dihydrogen and then ruptured situation, that isolated two hydrogen atoms, that is like just like a nascent hydrogen, and then this ethene molecule, okay, one of the reactants. So, what is happening, that you have got ethene, okay, you have got ethene and you have got hydrogen and say platinum surface. Okay, you are carrying out the reaction. So, what is happening, that your end product will be like this. End product will be this. Okay, so it is a saturated one. So, what is happening is that this this ethene gets attached to this metal surface. Okay. So, two linkages are formed, as I will show in the next slide, that these two there are these two carbon atoms, and then initially there was a double bond. So, that double bond is now absent, and now that, as if this double bond has been used up to form a metal surface to carbon bond. Okay. So, now the situation is that we have got isolated hydrogen, I mean not isolated, metal surface bound hydrogen atoms like nascent hydrogen, and adsorbed ethylene molecule onto metal surface. Okay. So, next what will happen, that in order that these hydrogen atoms should take part in the formation of CH bond, they should migrate close to this carbon or maybe this carbon, and they should come at a bonding separation, bonding distance, and after that they will make a bond. Okay. So, that will be shown in the next slide, that the hydrogen atom migrate to the carbon and form bond. So, what is happening, that this atom will migrate close to I mean this carbon, and this one will migrate, maybe this one will migrate to this. So, there will be a bond formation, because these linkages are not like true chemical linkages. So, these are like some physical force or maybe weak chemical force. So, this valency is not fully satisfied, like here this valency is not fully satisfied. That is why it is, I told you that these are like like nascent hydrogen. Okay. So, then what will happen, that this hydrogen will migrate and then these two will form bond, and thereby making a saturated ethylene system. Okay, you see that this bond is formed, and now since now this carbon atom and this carbon atom is their valency is saturated, okay, or full satisfied, there is 4 valencies are occupied. So, this now what is happening after this valency satisfaction. So, this initial linkage with, that is adsorption linkage, will be weaker, and they will, so it will happen that this ethane molecule will leave the metal surface, the saturated one will leave the metal surface. Okay. So, they will, these molecules will diffuse out to the gas phase. That is what happened, that initially they came here, made a linkage, they means this ethene, and then this hydrogen got bound to this, and then they left. This after this was hydrogenated. So, hydrogenated system leaves your metal surface. Okay. Now, what is a homogeneous catalysis? Homogeneous catalysis is a catalysis where your catalyst and your reactant, these two are in the same phase, but in case of heterogeneous they are in different phases. So, the celebrated example can be chlorofluorocarbons. Okay. So, these chlorofluorocarbons are the catalyst to decompose this ozone. Okay. So, ozone layer depletion, okay, the mechanism by which this ozone layer in our atmosphere is ozone sphere is depleted. How this is done, that mechanism I am just going to show it to you. Okay. So, chlorofluorocarbons are like CFCl3. So, chlorofluorocarbons CCl3F or maybe CF2Cl2, these are chlorofluorocarbons, also called freons. Okay. So, what happens that these freons, since this carbon is associated with fluorine, and these two are electronegative elements, fluorine is the highest electronegative. Okay. So, electronegativity is very high. So, what happens that this undergoes this reaction, that is CF producing CFCl2 radical and Cl radical. In the same way, CF2Cl2 produces CF2Cl and Cl. Okay. Let me write it over here, that CFCl3, okay, giving rise to CFCl2 radical plus Cl radical. Okay. This is one reaction. Another reaction could be CF2Cl2 giving rise to CF2Cl dot plus Cl dot. Now, this chlorine radicals will react with this fluorine free radicals will react with ozone with the following scheme: ClO plus O2 producing oxygen. And there is another option that this ozone, they absorb, what is happening, that they absorb ultraviolet radiation, okay, to give rise to the following reaction, that is they undergo reaction in presence of ultraviolet light. So, O plus O2, then ClO plus O giving rise to Cl plus O2, okay. O plus O3 giving rise to O2 plus O2. So, net reaction from this we can write 2O3 giving rise to 3O2. So, ozone is now broken into oxygen in presence of these, I mean ClO radical. Okay. So, all these happen in the same phase, that is the CFCl3 or CF2Cl2, these are gas. So, in gas phase this catalysis is occurring. Okay. So, this is one celebrated example of gas phase homogeneous catalysis. Okay. There can be acid catalyzed hydrolysis of organic ester as well, where this is a case, that is a case of homogeneous catalysis that happens in solution phase. Okay. So, this decomposition of ozone to oxygen has got enormous importance to this damage of this civilization, or maybe humankind, or maybe plant, animal, as a result of entry of your ultraviolet radiation. Okay. So, ultraviolet radiation means this ozone molecules, what they do is this ozone molecules generally absorb this UV region producing oxygen, and this production of oxygen to ozone and ozone to oxygen, there is a dynamic equilibrium. So, this dynamic equilibrium between ozone and oxygen in ozone sphere, so that is a at that height. So, there is a dynamic equilibrium. So, that equilibrium is destroyed. Okay. As a result of which, so ozone is continuously being used up to produce more of oxygen, and thereby ozone layer is depleted. So if we want to talk more about catalysis, that catalyst will speed up a reaction, but only up to a certain extent. Okay. So, classical example is metal surface catalyzed reaction, and why these reactions are of zero order kinetics, that will be clear over here. That if suppose you have got metal surface where, as I explained to you, that adsorption of say ethylene C2H4 and hydrogen takes place onto the metal surface, and then reaction proceeds to a given direction, to a specific direction. But suppose a situation that we have got 100 chairs in an auditorium, okay, and say we have got 90 students to come to take part in some lecture. So, it is possible that 90 can be accommodated because 100 chairs are available. Okay. So, you can keep on adding more and more students up to 100. So, beyond 100 it is not possible to accommodate any more. So, that means these chairs are occupied, the seats are occupied. Okay. So, therefore, further addition does not have any influence, I mean should not do anything extra, that is no additional student will be able to attend the lecture. So, same thing happens in case of this metal surface catalyzed reactions, that when you add reactant onto the metal surface, I mean say gaseous reactant, then these reactant molecules will first get absorbed onto the metal surface, and this adsorption will continue until this metal surface is fully occupied by these molecules, these reactant molecules. Okay. So, until and unless there is any any availability of vacant position, okay. So, no further molecule can enter onto the metal surface. So, that is beyond a certain point, addition of more reactant won't have any effect, okay, and the situation is a zero order situation, that you are keeping on adding more and more reactant. But since your metal surface is covered with reactant, so further addition will not put any more more reactant onto the metal surface. So, that means the reaction rate will go to a saturation, there is no change even if you add more of reactant. So, that is depicted over here, that you see that rate increases until the active sites are exhausted. Okay. So, initially when, so this situation, this active sites, active sites means the chairs I was referring to in a lecture hall, in an auditorium. So, this increases means still the chairs are getting occupied, that is why rate is increasing, but you see beyond this point no change, that means all the chairs are now occupied. Okay. So, after a houseful situation, rate is independent of substrate concentration, and as that is why this gas phase metal surface catalyzed, say, decomposition reactions are zero order in kinetics in general. Okay. So, that is the situation for a zero order kinetics with metal surface catalysis. So, what you can say that in case of heterogeneous catalysis, the catalyst and the reactant are in different phases. Adsorption, that is, then this molecule gets adsorbed onto the metal surface. So, adsorption, that is the binding of molecule onto metal surface. Okay. And this adsorption typically occurs onto the active side. Okay. So, not all chairs are effective, some chairs are dummy. Okay. So, you cannot occupy those chairs, maybe something like a broken chair, although it looks like a chair, but it is not safe to use. Okay. So, adsorption on the surface occurs only on the active site, and locations where reactants are adsorbed, locations are where the reactants are adsorbed and may physically and chemically bind to the surface of the metal. So, maybe a physical binding, physisorption, or maybe a chemisorption. Okay. So, these active site locations are the locations where these molecules are adsorbed. So, and this adsorption can be physisorption or maybe chemisorption. So, chemisorption is associated with a higher amount of energy change, and physisorption is associated with a lesser amount of energy change. So, not that much stronger bondage onto the metal surface. So, the hydrogenation of ethene to ethane. Okay. So, the reaction is thermodynamically favorable, that is delta H is with a negative value, and of course, with finely divided metals such as nickel, platinum, palladium, the reaction rate is found to increase very quickly, because that increases the surface area. That is, if you have got a bulk metal, say a 1 cc, 1 cubic centimeter of a metal, and then if you crush it into small powder, small particles in a powder, and if you powder it, then the effective surface area is increased. Like if we have a two dimensional description, that you have got a material of this sort. So you have got 4 sides, say it is 2 centimeter, say it is 2 in some units. So, this is 2, say this is 1, say this is 1, this is 2. So, what is the total length? of the outside length is 2 plus 2, 2 plus 2, 4, 5, 6. Okay. Now, if you divide it into this like this, that is, you have got two such small from rectangle you generated two squares. So, now it is 1, 1, 1, 1, 1, 1, 1, 1. So, what is the length, outside length, perimeter? So, 1, 2, 3, 4, 5, 6, 7, 8. So, now it is 8, initially it was 2, 4, 6. So, there is an increase in this. If you keep on dividing, and it is, of course, it is a 2-dimensional case. In case of 3 dimension, another dimension is added, then the similar situation will happen. So, that is why if you divide, that is, if the particle is finely divided, then its surface area is increased enormously. And surface area increased means you are increasing the number of active sites, I mean the number of chairs on which these ethylene molecules will occupy and will react with hydrogen, nascent hydrogen type situation. So, react with nascent hydrogen or like nascent hydrogen to produce your ethane. Okay. So, there are 4 main steps, okay. That is, the molecules must approach the metal. The molecules will come close to metal, like say this is your metal surface, say this is your molecule. So, I mean this is coming like this, say this is your molecule, say this is your surface like this, say this is your surface, and say this is your molecule. So, this is coming, that means they have to approach, these molecules will have to approach to the metal surface. Okay. So, this is one requirement, that they must approach the metal. Then this hydrogen and ethene will get adsorbed onto the metal surface, otherwise no effect. Okay. So, in normal case, if you do not put any metal or metal surface, no reaction happens. Okay. Next is hydrogen dissociates to form H2 dihydrogen dissociates to form hydrogen atom on the metal surface. The adsorbed hydrogen atoms then migrate to the adsorbed C2H4, okay, in an appropriate fashion, that there is a formation of linkage. So, react and then react, giving rise to C2H6 onto the metal surface, and then the product dissolves from the surface and diffuses out in the gas phase. So, this way the reaction occurs. So, these are the 4 main or key steps in the process of heterogeneous catalysis, that is typically this metal surface catalyzed reaction. It is a typical hydrogenation process. Next is we move on to another a very important aspect is photochemical process. Now, so far we have talked about here that you have got reactant, say one reactant, maybe in case of unimolecular reaction the same reactant A plus A giving rise to A star plus A, then A star is giving rise to product. So, this A star is basically the energetic energetic version or energy rich version of A, energetically excited, okay. Or maybe in this case you see the same molecule, same molecule or same atom, same species, better to say same species, 2 of the same species, okay. Another situation can be A plus B giving rise to your product, or maybe several of this sort. So, where you see that your reactants are, this is one chemical substance, this is another chemical substance, Okay. A is a chemical substance, B is another chemical substance. So, this is a reaction between two chemical substances. Okay. But in case of photochemical process, if I replace this by a photon h nu, it is generally denoted by h nu, Planck's constant into frequency. It is the energy packet associated with the photon. So, energy is coming in discrete packet called the quantum, and so photochemical reaction occurs where this photon is a reactant. So, say A plus h nu giving rise to A star. So, it is called the photochemically excited one, and then this A star will proceed for further reactions and so on. Okay. So, here this is a reactant, this photon is a reactant. Now, why does it happen? Because atoms or molecules, these are associated with a number of quantized energy levels. If you recall any quantum mechanics course, you will be finding that say hydrogen, if you recall Bohr theory, you will be seeing that postulates are like you have got nucleus over here, it is just like a solar system, that plus charge is over here and outside there are orbits, although orbit concept is a classical concept. So, now it is replaced by orbital concept, that is the probability density plot of electron. Okay. So, atoms or molecules, they are associated with a number of energy levels like this, which are those are denoted by these lines. So, energy is increasing this way. Okay. So, maybe this is the lowest energy, then gradually it increases. Okay. So, maybe these are all electronic energy levels. Okay. Now, if you shine, so this is a system. So, this system is having a bunch of energy levels. So, if you shine this system with radiation h nu, then if you recall Bohr theory, that there will be an electronic transition from here to here, which is possible only if this energy gap matches. So, if you supply a photon of this energy gap, then and only then the transition from here to here will take place. So, transition from a lower energy state to an upper energy state, and these are all quantized discrete states. So, you need to supply a packet of energy called the quantum, and this quantum will take this system onto the next higher level or maybe next to next higher level, depending on how much of energy you are providing. Okay. So, in general that happens, there are different situations also, but I am not going to talk on that. So, it is basically this reaction is initiated by a photon. Okay. So, photon is just like an initiator or it is a reactant as well, because this is destroyed after it hits your molecule, the energy is absorbed and it is destroyed. So, you may call this as a reactant as well. So, that means your system was at this energy level initially, you shine with h nu, you reach here with a starred means energetically excited, and then in this excited state this reaction this species will undergo several processes. That may be a physical process that does not lead to any change in chemical composition of your starting material, or maybe a chemical process where a new chemical species is generated. Okay. So, this photochemical process, it is the initiation of a reaction by light absorbed, and typical examples are photosynthesis. So, it has got a complicated kinetics. So, photosynthesis, and of course, reactions in upper atmosphere, like I told you, this reaction ozone layer depletion or absorption of ozone, I mean ultraviolet light by ozone. So, that is typically a photochemical process. So, schematically we can write a scheme like this, that the lowest state, I mean most of the molecules are having ground singlet state. Ground triplet state is possible for oxygen. So, oxygen is a triplet in origin. Okay. Triplet state means 2 electron spins are up maybe, and singlet means one is up, another is down. So, it is a singlet situation, and triplet situation is this, or maybe this. Okay. So, so let us start from singlet state. So, say this is S, since it is the lowest one, that is it is given S0. So, transition occurs say to S1. S1 means it is the first singlet state, of course, it is excited. So, therefore, it is S1 star. Okay. So, schematically it is written like S0 plus H nu producing S1 star. Then this S1 star may undergo several processes, okay, maybe physical process, that this excess energy is given back in the form of fluorescence or maybe in the form of phosphorescence. I am not going into the details of that, because that will be taken up in a separate course. Okay. That is a fluorescence or phosphorescence. Next, it is possibility that this excited molecule, this excited species, okay, will undergo collision with another molecule, and thereby this excited species comes back to the ground state and making your the other species maybe either excited, or maybe the excess energy is given out in the form of heat. Okay. So, that is called the deactivation, maybe collisional deactivation is a classic situation, or maybe photochemical reaction, that this S star giving rise to two radicals P dot and Q dot. So, it is called the photochemical reaction. So, first excitation, it is the energy absorption, then it is called your emissive de-excitation, which is called the phosphorescence, or it may be phosphorescence, it may be fluorescence. Phosphorescence is emission without change in overall spin, and phosphorescence is the an emission with a change in electron spin. Okay. So, details is we do not have scope to detail this. Okay. Now, next is next step could be collisional deactivation, that is just mere collision, like collision of gas molecules, okay, of which one is excited, another is unexcited, and the last one is photochemical reaction. So, photochemical reaction is a true reaction, and others are like phosphorescence, fluorescence, and collisional deactivation. These are generally physical processes that is not attended by any change in chemical composition of the system. Okay. So, number of photons you can calculate is the total energy which you are supplying to the system. Okay. Total energy which you are supplying to the system divided by the energy of a photon. Okay. Suppose you are looking into 347.2 nanometer photon. So, energy will be like this, and energy ultimately comes out to be this much of joule. So, if you supply with 100 joule, then this will be of this much of number of photons that you are supplying inside your chemical system, chemical solution. And if you have a 0.1 molar 1 liter solution, then you have got how many number of molecules? It is of the order of 10 to the power 20. Okay. It is of 10 to the power 20 means 6.023 into 10 to the power 20, and the other one is 1.7 into 10 to the power 20. Okay. So, if you divide this one, then you will be getting that only 0.29 is the fraction that is activated if all the photons are used up in true activation. Suppose if it is a 1-to-1 correspondence, that 1 photon absorbed means that is used up to activate the molecule. So, that is the limiting value is 0.29. Okay. So, it is just simple activation, that is A plus h nu giving rise to A star. Now, what is quantum yield? Quantum yield is the number, I mean reaction quantum yield. If we, since we are discussing here the chemical reaction, so reaction quantum yield is the point which we should focus on to. So, it is the quantum yield which is equal to number of molecules reacted divided by the number of photons absorbed. That means number of photons in and number of molecules out. Okay. So, number of molecules out will be on the numerator, and in the denominator number of photons in. Okay. So, that means it is the percentage or maybe the fraction of effective like absorption, means not all absorption lead to chemical reaction like that. If it is a true 1-to-1 correspondence, then quantum yield should be 1, or in some cases quantum yield has been found to be more than 1 as well. That I will be giving you an example at least to show that quantum yield is more than 1. It may be huge. So, quantum yield is the measure of the extent of reaction in terms of with respect to number of photons which you have added into this into your system. So, quantum yield significance, what is the significance? If you think of a 2Hi to H2I2 decomposition, okay. So, Hi, then this will be H nu, N means nu. So, Hi will generate H dot I dot is the initiation step, F is phi basically, maybe because of some font problem this F phi is coming as F. So, anyway this is phi is equal to 1, that means 1 photon in, 1 molecule broken. So, that is why phi is 1. Then it is the propagation step, it is the termination step. So, in your this primary phi is 1. Okay. But significance is that if you put 1 photon in, then you will in principle generate say 2 hydrogen iodides to get decomposed. That means you see 2 Hi is actually taking part in a reaction, although you have put only 1 photon. So, that is why overall phi is 2 molecules reacted because of 1 photon. So, therefore, phi is 2. For H2 plus Cl2 to H2 to HCl reaction, phi has been found to be 10 to the power 6. It is a very high value. Okay. So, it is a kind of chain reaction. It is a chain reaction. That is why it is very high. So, that means you just put 1 photon and n number of molecules will be decomposed. Okay. So, is phi constant? So, means what are the factors on which phi should depend? Phi depends on lambda, means why lambda? Because suppose if you are supplying this much of energy, not this much, this say less amount of energy, then these molecules will not get activated to excited to S1. So, this reaction will not take place. Okay. So, that is why lambda means frequency, it is ultimately frequency related to the energy. So, it depends on energy. Temperature is also an important factor, because if you increase the temperature, so these elementary reactions are modified, and that will indeed affect your overall phi. Solvent is a very important parameter. If you take a polar solvent, the answer is different than compared to a non-polar solvent. If you give more time, if you shine after shining, if you allow the reaction to go for long time, then what is happening, that you will be getting more of phi. Okay. So, next is rates of photochemical reaction. So, your Br2 plus H nu giving rise to BR. So, it is just a homolytic cleavage. Okay. So, as per definition, rate is 1 by nu I dnj dt, as I told you in first lecture. So, dn dt means number of molecules of Br2 that is broken. So, which is nothing but equal to phi is the quantum yield times Fa. Okay. So, that is basically Ia. Okay. So, ultimately n Br2 is V into, because it is a number of moles of Br2, which is nothing but your concentration into total volume, and that gives you overall rate of reaction is phi times Fa by V. Okay. Where Fa is the moles of photon absorbed per second. Okay. So, Fa is basically your intensity, number of photons absorbed per second. Actually, intensity per unit area should be there, but we are ignoring per unit area. That is why ultimately Fa is means you can write Fa is similar to Ia. Ia means intensity of absorbed radiation. Okay, you can write in this way. Finally, it is a very interesting aspect of photochemical reaction, that photochemistry of vision, that we can see, okay, we can visualize thing. Okay. So, there is a photochemistry involved here. So, the molecule, the effective molecule is this 11 cis retinal, okay, and this is in cis configuration, and this is all trans retinal. So, if you have the visible light, then this 11 cis retinal is converted to all trans retinal. So, just this cis one becomes a trans one. Okay. So, this cis trans isomerization happens. Okay. So, through a visible light, through absorption of visible light. So, absorption of a photon triggers a photochemical isomerization. So, this is an absorption of, by means of absorption of photon. Okay. So, isomerization happens between 11 cis to 11 all trans retinal. Okay. And this then triggers a cascade of structural and chemical changes, resulting an electrical signal to a brain. So, that electrical signal is the signal that translates the information that we are viewing through our eyes. Okay. So, basically the image information, okay, is transferred to the brain in the form of electrical, a bunch of electrical signals, and we see this, that is, we see whatever is in front of us, and this happens this occurs in visible light. Okay. It does not happen in ultraviolet, or maybe not in ultraviolet may happen, but that will damage other components, I mean inside eyes, but not by IR light, infrared light. That is why we do not see in night time, but dog or cat, they can see, they might have some different option. Okay. So, the trans isomer is regenerated back to the cis with the help of ATP. So, then it is coming back, okay, it is coming back to this with the help of ATP, that is some energy is needed to put this back to here. Okay. So, so it is a very interesting situation, that and this is a cyclic process, a forward reaction, backward reaction, forward reaction, backward reaction. So, if it is not taken back to here, then with time our vision should have been diminished, but it never happens. So, that means there is an opposing process, I mean not opposing, there is a back reaction. Okay. Opposing reaction does not mean that it opposes your vision. So, this back reaction, there is a back channel. So, that is why complicated reaction like sequential reaction, or maybe parallel reaction, or maybe opposed reaction are sometimes beneficial to us, like we see here that this forward process is good for vision, okay, and backward process is also needed to have a sufficient amount of 11 cis retinal, so that next time we can see, like suppose we are seeing something for long time, that means there must be a continuous flow of I mean the flow of the process from this direction to this direction, that helps in seeing, and also this direction, that is back reaction, ensures that after certain time this will not be depleted. That is, if it happened that it is with time eventually, say it is, if it is exhausted, then we should have seen something black in front of us. Okay. So, that is why this forward reaction and back reaction may be in a different path is very important. So, back reaction is another it is a consecutive reaction. So, but that consecutive reaction regenerates your reactant, and that helps the viewing process, that is vision process. Okay. So, so that is all about various types of complex reaction. It is also a complex reaction. This photochemistry of vision is a complex reaction. Okay. So, that completes our initial part of complex reaction. I mean complex reaction is completed. So, we will then in our lecture, in our next lecture, we will talk about this theories of chemical reaction rate. Okay. So, that is theories of reaction rate. But before that, what we have learned in this lecture, that what is catalysis and what is catalyst. Then we talked about homogeneous and heterogeneous catalysis. Okay. Then a classic example of heterogeneous catalysis is metal surface catalyzed reaction, that is hydrogenation of ethene. And homogeneous catalysis, one celebrated example is the depletion of ozone by chlorofluorocarbon, CFCs. Okay. Then we talked about this characteristic of this metal catalyzed reaction, why it is zero order reaction, and also this importance of this and also we talked about this photochemical reaction. We gave a brief introduction of photochemical reaction. We have not talked more on this, because photochemistry is a separate topic that will be taken up in a different course. Okay. Now, and one important thing is that we have just given an idea of this photochemistry of vision, that is the importance of studying chemical reaction. Why do we study? What is the importance of your consecutive reaction? What is the importance of back reaction? How does it help in some cases? Although in some other cases this side reactions may lead to some undesired product, may lead to reduction of your overall yield. So, that is not good for us, but there are examples like the photochemistry, the example which I gave to you in connection with photochemistry of vision. Here you see that this back reaction is very important to maintain the equilibrium or equilibrium concentration of both components involved in this process, that is 11 cis retinal and 11 all trans retinal. Okay. So, in our next lecture we will talk on these theories of reaction rate, and we will start from collision theory. Okay. So, homogeneous gas phase reaction that say two molecules are colliding. So, we will start from kinetic theory of gas, that the basic postulates of kinetic theory says that there is continuous collision between one molecule with another molecule, or maybe there is a collision between this molecule with the wall of the container. Okay. So, unless these two components come close to each other, there is no possibility of say exchange of atom or reaction, because rearrangement of atoms is basically chemical reaction. So, if they do not come close to each other, then the possibility is less. So, that is why it is necessary to have some collision, maybe at least for gas phase reaction, and this collision mechanism can explain many of the features of gas phase reaction. So, we will take up that we will take up those issues in the next lecture. Okay. So, till then have nice time. Thank you.